Hi all, in this lecture we will analyze RC series circuit using Laplace transform. RC series circuit means what? So we are connecting R and C, resistor and capacitor in series, of course together with the switch and the voltage source V. Okay, so now what will happen? Let us assume the switch yes, the switch is closed at time moment t is equal to 0. Okay, now please remember in this closed loop, the current is flowing through this resistor and capacitor because of this voltage source. That current is nothing but I of t, small I of t. Okay, actually this is also small v of t. We are writing everything with respect to t because it's in time domain. So now we have to write use some kind of analysis method. So for example, we can use the KVL, Kirchhoff's voltage law. So it means applied voltage is equal to all the voltage drop across the loop. So here we have the two voltage drops. So we can write, for example, IR, that is the voltage drop V is equal to IR. So I of t times R, that's what I have written here, plus the capacitor. So we are writing the voltage drop across the capacitor is nothing but 1 divided by C integral of minus infinity to t small I of t times dt. So I told you the capacitor will store the charges due to the current is flowing through the capacitor. So if you want to calculate all the charges together and make the average value, then you have to use the integration. So that is the special mathematical operator, and the time interval is minus infinity to t. Okay, so then we are writing with respect to the time. So this is called I of t times dt. Okay, so now the supply voltage, of course, that is V times U of t. That is, we can also consider as a step function. So V times U of t is equal to I of t times R plus 1 divided by C times integral of minus infinity to t times I of t dt. So now we can apply the Laplace transform. Um, So after applying the Laplace transform to this equation, what will happen? So now this will be a V divided by S is equal to, this will become capital I of S times R plus 1 divided by C times I of S divided by S plus Q of 0 minus divided by S. Okay, this one is just indicating the initial voltage or the initial charge in the capacitor. Okay, but if we assume the initial voltage is 0 in the capacitor, then this term will be gone. So then we will have only this term, 1 divided by C times I of S, capital I of S divided by S. Okay, so so now I convert this equation into like this. So what I had done here is I just made the Laplace transform of each term in this equation. So Laplace transform of this V, if I consider that as a unit function, then that became as a constant. So it became 1 divided by S. So that is nothing but V divided by S. V is a constant here. Here I of t times R. R is a constant. And the I of t became capital I of S. And similarly here 1 divided by C is a constant. And when you do the integral of this I of t, then it became capital I of S divided by S. Okay. So before we go into more problems by using Laplace transforms, you have to know three important properties of Laplace transform or LT. So the first one is called linearity property. So linearity property, what it says, so capital L of L means nothing but Laplace transform. So Laplace transform of A times f1 of t plus b times f2 of t. F1 of t is a function in the time domain. F2 of t is also a function in time domain. So how it becomes? So it becomes A times capital F1 of S plus b times capital F2 of S. So if you Laplace transform this specific term, then it will become like this. and this is called linearity property. And time differentiation and time integration, there are two more properties. So time differentiation property means, so now we have the differentiation term, and now you want to do the Laplace transform on this differentiation term. So L of d divided by dt times f of t. F of t is the function. So it becomes like this. So s times capital F of s minus f of 0 minus. So this 0 minus is indicating the initial source. So that is the, remember here, the initial source of the inductor, for example, is always minus, starting with minus. So anyway, here now we are not really talking about the inductor. So now we are talking about the property of linear transforms. If you look at the formulas from Laplace transforms, then you will see all these properties. So now we are seeing the most important properties which we will use very often in all the problem solving further today. So now the differentiation, time differentiation. So if you Laplace of this term, then it becomes like this. And the time integration. So Laplace transform of integral of 0 to t small f of t dt. So then what will happen? So 1 divided by s times capital F of s. So if you integrate like this, then it will become like this. So exactly, this is very important. That is what happened here. So small I of t, it became capital I of s divided by s. If you apply this time integration property in this formula, that's how I wrote like this. So always remember these three properties at least, or you can also refer the Laplace formulas. I'm sure you have studied about Laplace transforms, Fourier transforms, Z transforms. So all these transforms which we will use practically in the circuit to analyze the signals, signal processing. Okay, so now we have already converted this equation, time domain equation, into the S domain equation. So I also assume there is no initial voltage or initial charge in the capacitor, so we can ignore this one. So now I can rewrite this equation here like this. So V divided by S is equal to R times I of S plus 1 divided by CS. The S I just take it outside, and times I of S. So now I of S is a common in both terms. So I take the I of S as a common. So I of S times the bracket, within the bracket, R plus 1 divided by CS. So this is the equation now we are getting. So this is the final equation we got in the just before. So now what I am going to do is, I want only I of S because I am after the current in the loop. Remember, so I am doing the analysis. I am finding the current in this loop, small I of t. Of course, this is in the time domain. Now I am converting into the S domain. So this became capital I of S. That is what I want to find. So I of S, I am keeping the I of S like this, and then V of V divided by S, I am bringing this term to the other side. So V divided by S times R plus 1 divided by CS. I'm just rewriting this equation in this way. So here, whenever we have this kind of equation, we have the upper part is called the numerator, the bottom part is called denominator, and the center one is called fraction bar. I just would like to highlight this numerator, denominator, and fraction bar because I'm going to use this term very often in further problems and analysis. So the upper part is numerator, the bottom part is denominator. Okay, so now we have the equation like this: V divided by S times R plus 1 divided by CS. So you have to divide both numerator and denominator by R. So you are going to divide the numerator and denominator by R. So V divided by R divided by, so S times R divided by R is nothing but 1 plus 1 divided by RCS. So I am writing the same equation little bit differently. So if I divide r in both numerator and denominator, then it's equal to, I am not using r. So now I just, for a simplification, I am using this technique. So now I of s, remember left side we have the I of s. I of s is equal to v divided by r. So now we have s right in the common. So I'm bringing the s inside. So then s plus, so s will be cancelled. So 1 divided by rc. So this is the final equation for this RC series circuit. So now I have found the current which is flowing in this RC series circuit. I of S is equal to V divided by R whole divided by S plus 1 divided by RC. So this is the required Laplace transform of this RC circuit. This is the final answer. But remember, we do not want to stop just like this. We need to again convert back into the time domain. So it means I have to perform inverse Laplace transform. So what we had done was, we have written the circuit equation in time domain and we did the Laplace transform and it became like this. And then we are simplifying mathematically a little bit. And then finally we got the equation. Now I have to perform inverse Laplace transform again and then convert back into the time domain. So if I make the inverse Laplace transform of this capital I of S, then it will become I of t. So V divided by R is a constant. I just take it outside. So here how it will look like, 1 divided by S plus 1 divided by RC. So this is the equation. So now it is like this. We know 1 divided by S plus A. So what is the formula of Laplace transform formula? Do you remember? 1 divided by S plus A. Please try to look at the, try to remember the formulas. If you do not remember, please look at the formula list. Yeah, so then you will find this equation in the other way. So now if you apply this inverse Laplace transform to this equation, it will become like this. So small I of t is equal to V divided by R e to the power minus 1 divided by RC times t. So here minus 1 divided by RC. So because the formula is minus e to the power minus a times t. So here the a value is nothing but 1 divided by RC. That's why it became minus 1 divided by RC times t. So this is the required inverse Laplace transform of the RC circuit. So by this way, you can perform the analysis of the circuit by using Laplace transform for any circuit. So now we had seen only the RC series circuit in this example. What did you learn from this problem, RC series circuit? Remember, so I already told you 3 steps. The same 3 steps we followed in this analysis. So we replace each circuit element with its S domain equivalent. So you can draw the circuit or you can just write the equation. So the initial energy source we considered, for example, in the previous example, the RC series circuit, we do not consider the initial voltage source. So for example, here I wrote the equation, but I have removed this because I assumed the initial voltage in the capacitor is 0. So I removed this, but you have to write that. The standard procedure is like that. Okay, so either you can write the initial source as a series source or parallel source. So we have used series and together with the element impedance. So element impedance is nothing but the C value. Okay, so now and then we have written the equation, the KVL equation for the circuit analysis. And then we have transformed the equation into the Laplace domain, from the time domain into Laplace domain by using the Laplace transform. Remember again, so we have first written the equation in time domain and then we use the Laplace transform and we convert the same equation, the notations into the S domain. And then finally, we have also converted back the same equation into the time domain by using inverse Laplace transforms. So these are the 3 steps. Remember here, again, we use the inverse Laplace transform and brought back the equation into the time domain. So we have first written the equation in time domain and then we use the Laplace transform and convert into the S domain, and then we did perform some mathematical simplification of the equation like this, and then again we use the inverse Laplace transform and bring back the equation into the same time domain. So this is our final answer. So we have two answers, important answers. This is the final answer in the S domain, and this is the final answer in the time domain for RC series circuit. So these are the three steps which is common for any circuit you have to use.